All right, let's get started. Welcome everyone to today's webinar, whatever time zone you find yourself in. Our webinar today is entitled Create Safe Life Environment. My name is Dale Berry from the Dassault Systèmes SIMULIA brand marketing team. In today's webinar, we're going to highlight the use of SIMULIA computational fluid dynamics solutions to help understand and learn about and mitigate the propagation of virus droplets within the social spaces that we're going to be emerging back into shortly. As we all know, we're beginning to come out of lockdown, and so this is a particularly important topic given the situation of today. We have two speakers today. Adrian Mann joins us from the Industry Process Solutions team in SIMULIA. As well as his colleague, Emmanuel Vinoli, is also going to present one of the sessions a little bit later. So the Industry Process Solutions team is our field team that is devoted to working closely with customers to help convey the value and the promise of our solutions to our customer base. So next slide. Before I pass the ball over to Adrian, let me say just a word about the webinar series that we're conducting. Dassault Systèmes has an entire series of webinars under the label Business Must Go On. And as you can see, this is the story number 7. Last Thursday, a week ago, we did story number 2, which was about co-design with CATIA V5. All of these stories are united in the fact that we're talking about using technology and Dassault Systèmes solutions to help people be productive in their work from home environment. You know, working from home is not just about reading email and joining Zoom calls. It's really about being productive and innovative. And you're certainly going to see that in today's story, where a team from China made a large contribution to the COVID situation there. So with that, please join in and enjoy the rest of the webinars in this series. The replays will be available for you to take a look at as well. So I'll pass the ball over now to my colleague, Adrian Mann, who will begin the technical portion. Adrian?
Thank you, Dale. So good morning and good evening to everybody. So today, in this Create Safe Life Environment webinar, I'll be talking about a few things. We'll be talking about how we're using our fluid solutions to really reveal the invisible. So looking into how COVID-19 and in general, viruses or contaminants propagate into our life environments, and how you can leverage simulation to minimize the risk of contamination in an area. And so we'll talk about several examples, real examples, and more like say case studies that are going to be looking into this specific topic. And then we'll go through a live question and answers for any question you might have from the webinar. So the first thing to talk about is basically looking at what has been the impact of COVID-19 so far. I mean, it's clearly a global pandemic. As I was preparing this, the content for this webinar, I've been writing down these numbers, and every day, the numbers were changing. So it's a very challenging time for humanity in general, and finding ways of working against the coronavirus pandemic has been one very strong activity for SIMULIA in Dassault Systèmes. So one of the topic that we've been involved very early on is when China was trying to cope with the number of people that were basically affected by coronavirus. And so our team in China has been very responsive, helping the Chinese government in constructing hospital in a very quick turnaround time. We're talking about a few weeks to be able to design and build a modular hospital. And one of the key topics here was to make sure that you know, the airflow, the ventilation system of this modular hospital will be able to extract the contaminants from the rooms to prevent further infection from people. And so for this specific work, our team leveraged SIMULIA X-Flow to look into the transport of the contaminants into rooms, and finding out the best layout of the inlet and outlet of the HVAC system to extract the contaminants, and also looking into how the extraction chimney would be propagating the potentially contaminant through the surrounding city, and making sure there's a minimum risk of contamination. So the work was really great. I mean, it was basically done in less than a couple of weeks to maximize, to minimize the risks. And the Chinese government sent you a thank you letter for helping us on this topic. So it was really overall a very human success story, in sense of making sure that designing those hospitals would be, helpful for the population, and in a turnaround time that would be matching the crisis. So, of course, there is a human, let's say, the human impact. There's also the economic impact, and that's something that we're going to see. I mean, we've started seeing already. On the first quarter, you just look at the global economy; it's been reducing about 5% already. Because the second quarter, we're already a month and a half in the second quarter, and most countries are still confined. We'll see another impact in the second quarter. And now the question that is on everybody's mind is, okay, we're going to be deconfining. How can we ensure that we're doing it safely? How can we make sure that when we're going to be returning to work, when we're going to be reopening the factories, how we make sure that those factories are going to be safe for everybody? Same thing for the schools. I mean, that's going to be an important one. I mean, right now there's a lot of discussion about delaying, the school, going back to school to September. But obviously, this September, we don't know where we will be. So there's going to be still the question of how to make sure that we're all safe. One of the big one is air travel. I mean, right now, it's very difficult to travel from one country to one country. But when this is going to be happening, how do we make sure that the aircraft are going to be safe? How do we make sure that the airports are going to be safe? So those topics are very important. And then in the end, also, a lot of the economy, the services economy related to restaurants and bars and all the things that we love to go to, the movie theater, we have to make sure that those are safe, so that then we can actually go back to the normal life, and first of all, to be able to do what we were used to do, and also in terms of releasing the economy from the impact of the crisis. So now going a little bit into the technical aspect of COVID-19. So what it is and the transmission path. So really I think a lot of everybody is aware of coronavirus, about what it is. I mean, it's a virus that's propagating through people coughing or sneezing, or even potentially breathing. So basically, when we're coughing, for example, we're releasing droplets that are potentially contaminated. And those droplets are going to be either, let's say, be transported by the airflow of the cough, or they're going to be also, depositing on surfaces, and then in the end being basically leaving the virus, can live from a few hours to a couple of days on surfaces in various areas. And so, there's the risk of infection by touching a contaminated area and then touching your face and potentially be contaminated. One of the things that we're going to see in this discussion is specifically, the lighter droplets that are being emitted from coughing, and how they are actually being transported by the airflow around us, and those can be, a risk of contamination, because they can go further than typical guidelines regarding the distance from people, from each other. So on our side, over the 1 or 2 months that we've been basically working really hard on this topic, we've been working on specific methodologies to be able to simulate a cough, simulate a sneeze with a very high accuracy, and also other methodologies to be able to look at it at the scale of a very large building, of a factory, and this type of thing. And so we started by looking, into literature, published literature about, what is the airflow that's generated, when you're coughing. What is the distribution of the droplets that you emit when you are coughing. And basically, as I was explaining, there's two different behaviors. When you have the large size droplets, which are more about 0.7 micrometer, they're going to be actually falling off on the floor due to gravity. There's still going to be an impact of the airflow around you, but they're going to be mostly falling off. And then the smaller size particles, actually, which are typically of the same order of magnitude of the virus diameter, they're actually going to be carried away from the cough airflow, and this is something that you will see in the video that we'll be showing. And there's a very complex airflow rate profile that we've been implementing into the software, which is causing the flow to be highly transient and turbulent, regarding the impact. So you can see, already here the actual airflow coming from the lungs, going through the mouth and being expelled, and that's going to be carrying particles as well. So now when we look at the modeling, we have two types of advanced modeling, and this is the type of work we can do with our very good CFD solvers that we have in house. So the first advanced modeling is really looking into the particle tracking. So in this specific case, we're actually looking at tracking all the droplets that are being generated from coughing or sneezing or breathing, and leveraging the fully transient and turbulent CFD solver SIMULIA Power Flow. With our particle tracking technology, we are able to look into the propagation of the droplets in the environment. So this is like for an area where there's no airflow and you're basically just expelling the particles, and you see them basically flying away, transported by the airflow of the cough. And then on top of it, we have a surface droplet deposition model that allows us to identify which surfaces are going to be contaminated by the cough or the sneeze. And then we have also a simplified modeling that is leveraging the scalar transport technology. So in this specific case, we would be basically paying attention only to the lighter droplets that are going to be transported in the air, just like aerosols. And in the specific case, we can leverage SIMULIA Power Flow, we can leverage SIMULIA X Flow, depending on the situation, and again, this is a fully transient turbulent CFD. So when we look into other examples of an hospital, for example, that we covered by Emmanuel, you'll see that it's also showing the propagation of the aerosols within the floor, within the building. So the first step, it's one of the important steps that we took, is to do really a validation. So here I'm not showing the comparison to the experiment because it's published data, and we wanted to point you to the published data so you can actually look into it. But basically, we've been looking at the time evolution of the cloud of droplets that is already emitted from coughing. And also, the geometrical characteristic of this cloud, and we've been comparing this data with the published data in terms of what's the actual shape of the cloud and the geometrical parameters of the cloud as time goes by, and we observe that we have a very good correlation between the two. So it gives us the confidence that when we're leveraging a turbulent solver to solve this kind of problem, we are basically able to get closer to reality. So, of course, there are assumptions in what we're doing. So I wanted to mention them. So the first one is that all the droplets that we are emitted are not necessarily contaminated. So the virus size is about 0.125 micrometer. So when you are coughing, some of the droplets that you're emitting might be smaller than that. It doesn't mean that the virus is not, in some way connected to the droplet, but obviously we don't have necessarily information about the contamination rate. So if you had the contamination rate of the droplets, you could start deriving statistics from the simulation data. And those are the information you could get to get information about the risk of propagation. And of course, I already talked about that, but when you're using scalar transport, then you're neglecting the impact of the larger size droplets, because you're going to look only at the one that are behaving like aerosols and being transported away. So in the end, the outcome is that we can leverage both solvers to do an assessment of the risk of propagation of the virus if we're assuming them to be contaminated. There is also, the fact that those contaminated droplets can or cannot contaminate someone depending on the virus load that the person is going to be inhaling. And those are topics that we keep looking into because we want to make sure that we're providing the right answer to people who are concerned about this topic. And in the end, what we recommend is that if you want to do a quantitative analysis, you can use SIMULIA power flow with particle tracking. And then when you want to do a qualitative analysis, doing a risk assessment, seeing the impact of changes in your layout of an office, of a factory, some safety measures like wearing a mask, or protecting the people with glass panels or plastic panels, these type of things, then you can look into this with scalar transport with SIMULIA power flow or SIMULIA Xflow. And all of this, those solutions are available on the cloud, so it makes it very easy to access them. Now, on the technical advantages, both power flow and Xflow are lattice postman-based methods. What does it mean is that when we're solving transient problems, like we need to here because of the aspect of the transport of the particles, it's about 4 times faster than Navier-Stokes based solvers. So this is an important fact when you want to actually use those methods those transient solvers to solve the real problem. And because it's fully transient and turbulent, so you're going to capture accurately the transport of the fine particles, and you will also have good details of the airflow that is going to be generated by ventilation systems, even if it's larger scales, and that's going to also impact how the actual droplets are going to be transported around. And then another benefit of this lattice postman-based method is that there is no need for geometry defeaturing like typical solvers, and that means that you can spend up to 3 times less time in geometry preparation to get to the result. And that's really how we were able to provide answers for the hospital in China, in the Wuhan province, in less than 2 weeks. And that's how Emmanuel will talk about how he was able to provide the results to an hospital in France the same way. So now, regarding the efforts that we've been leveraging and pushing at Dassault Systèmes in general. So we created this community on the 3D Experience platform to invite all the thinkers in the world to work on the topics to help fight this pandemic. There's been a lot of topics around personal protective equipment, around ventilators, and this community is public. I mean, if you wanted to look into it, you can register on the Dassault Systèmes website. And one of the topics that was looked into was the face shield, right? When you're using personal protective equipment and the face shield, and how efficient they can be in terms of their design. And so really looking really deeply into this, we basically helped the community with simulation, looking into what is the best design for a 3D printed face shield to protect the people, at least as much as possible against a potential contamination. So we investigated 4 designs that were associated that were 3D printable. I mean 3 designs that were 3D printable, and then a larger protection to show that it's maybe important to go further to be able to protect people. And you can see the 4 designs here. So one was not covering the head; it was really just supporting the face shield itself. And then you had an headband spoiler to try to protect the front head against the droplets, and then a headband cover which is more like a flat area that's trying to protect. And then the last one was a larger protection with a face shield that was covering more the side of the face, and also had a good protection of the front head against droplets. So now looking into we applied our methodology with particles to look how when someone is coughing or someone is sneezing, how it can be impacting how can it be behaving in front when it's basically the droplets are going to be projected. And what we observed is that even if you have a face shield, basically, because of the difference of pressures between the flow going onto the face shield and the pressure behind the face shield, we observed that some of the particles are actually able to go behind the shield. And if you're not wearing a mask on top of it, you have the risk of basically inhaling those particles. So it's very important from this observation that the face shield is going to go lower than, as low as possible, and also that you wear it in combination with a mask. I think that's really key for the protection of people. So those things are being learned. So, looking at the contaminated area, obviously, the face shield itself is very much contaminated with droplet deposition from the cough. I mean, that's the main purpose of the face shield. So on that side, it's doing a good job. Now, if we look beyond the face shield and we start looking at, where are the droplets being deposited on the face of the person that is wearing the face shield, we see that the actual front head is pretty much covered with with a lot of deposition for the first design. It's a little better when you have a spoiler on the head. But the best design that you find is that when you're covering more of the face and also you're protecting well the front head to prevent the airflow from basically coming close to the head, and also pushing it away from the front head. So that's really giving you an overview of how you can leverage the simulation and the surface deposition model to look into which area is going to be contaminated for people. And we look at further example afterwards. So, from there, I will let Emmanuel walk us through another story about a different hospital and how it was a personal story for him and how it impacted how it had an outcome for safety.
Thanks, Adrien. Can you all see my screen?
Yes, go ahead.
Okay. We just put the chat on the side. Can you see the chat, or can you see only my presentation?
Go ahead. You can see the video, right? Just
okay.
Use
Good.
our presentation. Yeah.
All right. So I was personally, touched by the coronavirus at the beginning of March because my parents and my grandmother were contaminated. They are living in the northeast of France, and northeast of France was highly touched by the coronavirus, and that's why we wanted to see if there was a way to help the hospital during this hard time, and thanks to the community. We were able to help them in two ways. The first one was the fact that they were facing a lack of production material, and we were able to put in contact local makers with the hospital and provide good face shield, in fact, for the hospital based on what Adrien just showed in terms of study. And on the other hand, we were trying to help them with something more serious than protection material. So the expansion of the number of patients contaminated by the coronavirus was very, very huge and quick in this hospital, and in a few days, the area where were healed the patients just exploded in terms of surface, and at one point it was really close to old people care nursery, and the director of the hospital had a concern about a risk of contamination from the COVID area to the COVID-free zone, and that's why we decided to provide him some simulation. The first one was to do a risk assessment of the current state of the hospital floor. And then if a risk were highlighted by the simulation, why not trying to help them with a very simple solution? And this is what we will talk about in the coming slides. So we started from a PDF file because, as you may know, hospitals are not, industries like automotive or aerospace, and they don't have a 3D model of their hospital. So we started from a simple PDF file with very simple information about all the ventilation system of the floor. For example, we had the information of only one ventilation per room. It was only air extraction. We model in a simplified way the leakages from the windows. Is the red rectangle that you can see here, and we decided to go in a worst case scenario, meaning that we took the assumption to consider the COVID as an aerosol, and all the patients in the COVID area will kind of cough 100% of contaminated air at several times during the simulation. And the goal is to track in the space and in the time how this contaminated air will evolve in the floor and see if there is a risk of contamination. So the COVID area is the area in yellow, which you can see in this slide in the middle. Just to have something in mind, let's say in day 0, the COVID area was the square on the bottom, and 5 days later, it was all this area in yellow. And the area to protect is the one in the red circle here. So as I said, we evaluated a worst case scenario with all the patients coughing in the same time, and a modelization of aerosol from the COVID-19. So what were the results? Here you have 2 videos on the right. On the top, it's a kind of contamination ratio in the air. Here is in between 0 to 10% of the air contaminated by the virus. And on the bottom, you have a simple visualization of the flow field velocity, of the air velocity. And unfortunately, what you can see in this video is the fact that the natural flow path of the air is to go from the COVID area to the safe area. Why? It's because of the way the ventilation system is built. We have more ventilation system in the safe area, and it will induce pressure gradients going from a high pressure area in the COVID space to the low pressure area in the safe zone, meaning that the flow will naturally travel from the COVID to the safe zone, which is not a good news. So making this risk assessment, we try to figure out how to help the hospital with very simple solutions. So the goal was not to say, hey, we need to rebuild the full HVAC system because it's not working the right way. No, the goal is to provide a very quick solution that can be used directly after the simulation. So that's why we decided to go for 2 scenarios. The first scenario was to evaluate if it was possible in the hospital to reduce the ventilation system level for all the safe area. You have to know that this safe area is in fact old area of the hospital. So the COVID area is a new one. It was built in 2006, and so we decided to try to see what could be the impact of reducing by 50% the ventilation system in the safe area. And we had a good let's say answer from the simulation, because by doing this we are putting a good equilibrium in between the safe area and the COVID area, as you can see in the pressure field on the right of the slide. And if you look at the contaminated particle ratio here, then you can see that there is less particle that can travel to the safe area, and it seems that after 4 minutes of physical time simulated, most of the particles are contained in this room here, which is in fact the stairs of this floor. So this solution was a simple one, but it was working much better than the current state of the hospital. The other solution we wanted to evaluate sorry, was the impact of opening windows in strategic position. So as you can see on the video of the scenario number one, we have contaminated particle in the corridor, and this is in fact the main propagation vector along the hospital. So which makes sense because it's logical. But in this case, the goal was to reduce the contamination in the safe area, but in the meantime, trying to protect the medical staff by reducing the contamination ratio in the corridor. And that's why we opened two strategic windows, as you can see in the circle on the top left of this slide. One in the middle of the COVID area to really try to create a flow field that will break, in fact, the natural flow path of the air, and the other one in the safe area, and in order to create a kind of aerodynamical blockage by creating an acceleration of the air with the opening windows. And this is basically what happens. In fact, if you look at the velocity fields here, and in the meantime, if you look at the contamination ratio of the particles, you will see that the safe area is now much more protected than it was in the current state of the hospital. And in the meantime, thanks to the opening in the middle of the COVID area, we are pushing basically the air on both sides, but especially on the square where COVID patients are ill, and we are reducing a lot the contamination in the corridor. And this is basically the solution that the director of the hospital is using right now to protect more the medical staff. So just to finish about this story, because I think it's very important to see what was the feedback of the director, and because I think it's nice information that could impact not only hospital but everybody and every industries and everyone here. So for him, the very important thing was that thanks to the simulation, he was able to understand how the flow field was traveling in his hospital quickly, and then he understands basically the risk of the contamination in the corridor, for example, the risk for the safe area. And what was very valuable for him is the fact that in days, because we are talking about less than 1 week to perform the simulation from the PDF file to the scenario number 3 here, he was able to find a solution that can be applied directly to his hospital. So it was very valuable for him. On the another end, what is very important to him too is to use this simulation and all the animation that we are providing to show that that amount of information to the medical staff and try to, explain them why they should not remove the mask in the corridor, how they can maybe rethink about the layout by moving common spaces in other area because it could be in a risky area. So all this kind of information is basically providing some hints to improve the protection of the medical staff and the public, and this is why I think it was very, very valuable for everybody. The next steps, we are planning to do measurements in the hospital, pressure measurements, thanks to other companies in the east of France and a local university, and see if we can find a correlation between what the simulation is showing and the reality in the hospital. And the other next step is that we are currently working with a Parisian hospital in a similar way, but just to prepare what will be the situation after the peak of contamination of COVID, when people with COVID-19 will have to live in the same floor with other people during the summer, so when ventilation is on, and they want to understand where are the best area, to put safe people and contaminated people. Thanks.
Thank you, Emmanuel. Can you, just to confirm, you can see my screen properly, right? Because I think I had a little of a connection issue. All right, so now, looking into the various applications. So I mean, great story, Emmanuel. I think that you're absolutely right. Looking into this information is very valuable for our hospitals. I think that we also have a lot of value looking into how can we ensure that the various areas where we work, where we live, are going to be going to be basically open for we can reopen them with in a safe way. So here, again, some examples of if you're walking into an office, how the particles are going to be basically, from someone sneezing, how they're going to be depositing and how they're going to be traveling in the office, over time. And you can adopt some gesture that's going to be helping at least for the surface deposition. But if you look at the video here, you see that the droplets are actually flying off, and the lighter ones are actually going upward, which can mean that they're going to be propagating further. So they are like those type of assessments can be done through simulation. And the first step is really, we need to assess propagation and contamination risks. I mean, that's one of the key points to solve. If you look at the videos on top right, this is going to be for a longer time, and you will see that, all the light particle actually over time from the ventilation system, it's basically carrying it around. They are being dispersed over steered and dispersed over the entire office room. So clearly, when we talk about aerosols, instead of just being large droplets being projected on the surfaces and people, then you need to start looking at the scale of an entire room or an entire floor to assess, what is the possible contamination of an area. And okay, moving forward, the first step is going to be to look into safety measures. Moving forward, it's going to be about looking into improved HVAC systems with recirculation system filters to clean the air so that we can prevent this type of problem. And of course, one of the key points here is that most of the time we focus on the thermal comfort, cool air, hot air, to keep us comfortable. But usually this is achieved by thermal mixing, so by mixing the air and so that the temperature becomes even in a room, and that's actually helping propagation of contaminants. So this is something there's a trade-off between the two that can be worked on for simulation. In a similar way, if we start looking into a vehicle cabin, in a car or bus or other type of transportation, we can have the same type of problems. And actually, when you're just cooling down the cabin, you're losing the airflow from the front vents. What we observed that if someone is coughing into a car, in a very short amount of time, the entire cabin is basically filled with those aerosols, and basically there's going to be a deposition of even the larger droplets all over the car, making it, making a lot of the surfaces being contaminated. So obviously there are several ways to cope with this. I mean, the first one would be to wear a mask to minimize, the number of the amount of droplets that are being actually propagated outside of inside the car. And then, of course, about cleaning the surfaces of the car, and you can identify, which areas are going to be needing cleaning. And one thing that's, it's been more and more used in the industry has been those very high capacity filters, which are used to clean the air for recirculation. And this is where, simulation can help also to make sure that those are as efficient as possible when it comes to taking those particles and treating them. And that's really, moving forward, the ability to look into the airflow of the cabin, to achieve the comfort in the cabin in terms of temperature, and at the same time making sure that the viruses, but also the dusts, the contaminants in general are properly filtered by the HVAC system, so that the air is actually clean inside the cabin as much as possible. It's all about minimizing risk in the end. And then the last one, to talk about is air travel. So, this specific one has several aspects. I mean, you have the airport, you have the airplane. How do we make sure that those areas are safe? Airplanes have very sophisticated air cleaning systems. So simulation can be used to make sure that when the aerosols are being emitted by people, they actually quickly go through the recirculation system and basically removed from the air of the cabin. So that's one thing to look into. that can be assessed with simulation and also improved. And then, of course, when you look into the airports, you can start looking into which areas are going to be contaminated and which areas maybe some areas are not going to have enough airflow to clean up the air in the long term. So that there's going to be a minimum concentration of virus if some people are sick in the airport. So you can optimize the flow of passengers, and we have solutions for that from our Delmia brand. To look into the flow of the people through the waiting lines and how to optimize this for both for efficiency of the people boarding and also for the safety of the people in the airport. And we'll have two webinars next week, one for the airports and one for the airlines. That's illustrating this into more details. All right, so to conclude, some of the key takeaways here. When it comes to going back to normal life, we're going to need to assess, the safety of our living place and maybe, decide some measures to make them safer. And that's going to be, about reopening all types of things. We talked about the factories, we talked about the restaurants, you could talk about movie theaters, airlines, airports, all of these areas. And we believe that, the CFD fluid solutions of SIMULIA, they've already have offered the ability to assess the risk and to design changes, not necessarily in the design of the ventilation system, but some measures that can be taken to mitigate the issue. So we've already been using this both for the hospital in China and the story that Emmanuel just told. And of course, in the future, when we're looking into the design of buildings, the design of vehicles, aircraft, those solutions can also help out building better and more efficient systems so that we can minimize the risk of a pandemic in the future. And we're here, we have some expertise, and our teams, they're ready to help on this topic. And we have a worldwide team that can support on assessing those risks, leveraging the technology that we discussed into this presentation. So one thing I wanted to finish with, I really want you guys to stay safe. We've revealed in our story, that the smaller size droplets can actually get airborne and travel further than 6 feet. So the 6 feet rule is a must. It's something that really minimize risks. But of course, it's not necessarily enough. And if you wear a mask, that's going to be already better. And that's not just to protect yourself, it's also to protect others, because you might not have any symptoms and you'll be carrying the virus. And from the studies we just looked at, I think it's important. So from there, thank you for your attention, and we'll take some questions as they come. Right, let me bring up if we have some.
Dale, I think you cannot hear you.
There we are. Sorry.
Okay.
Thank you, Dale.
So thank you, Adrian, and thank you, Emmanuel. It's a great case study of how simulation really is able to inform us about what's happening in the world around us, particularly when there's really no other alternative. So yes, let's turn to some questions. We have some that have come in from the audience. The first question is about droplet interaction. Do you have to assume that the droplets do not interact with each other? I mean, you do have a model to tell you where the droplets are deposited. How about droplet interaction?
Thanks. Yeah, that's a good question for the particle tracking. So yeah, we do have some coalescence model that can help, if the particles are actually bumping and they might be changing, the coalescing together. So we have this this ability, and then we also have I didn't talk about this, but when we look at surface deposition, you can choose that the particle is going to be actually sticking to the surface. It can also be splashing. So it's not a simple particle tracking model. It's really a particle tracking model that's aimed at working with liquids and how they behave with surfaces and as a liquid in the air. And that's because we've been using this technology for many years now already in the transportation mobility industry to model sprays, to work on water management problems, when coming to the windshield and this type of work. So we're confident in the technology from this, and then we basically turn it and applied it for this life science topic around sneeze and cough.
Excellent, thank you. All right, next question is about the particular tool that was used in the hospital air circulation project. Can you clarify what the tools were and what methods were used in that project?
Okay, so for the hospital simulation, we used power flow with passive scalar model to track, in fact, contaminated particles in the simulation. So it's a, let's say, a more simple approach that's what Adrien just said about droplets, but it's a good way to simulate for, let's say, in a quick time, a very large model like an hospital. I think for this project we could have used also Xflow because it should be okay also in the meantime for this kind of project. But since PowerFlow was the tool I know the best, this is the one I choose.
Yeah, so
Okay.
just to build up a little bit on that answer, you know, the hospital in China, it was Xflow. For the hospital in France, it was PowerFlow. Both were able to bring the solution, you know, the answers to the question that were needed. So I think both tools can be used on this specific topic, at least for large scale transport with some assumptions. Yeah.
Okay, very good. And I think that is the extent of the questions. If you have any other questions, please enter them into the question box right now. Otherwise, Joanne, if that's, oh, there is one more. Here we go.
Yeah.
So the question is about the total time simulated. How is that defined? How do you decide how long you have to go? And what does that imply about the efficiency of the simulation that you're running?
So for the hospital simulation, we simulated 4 minutes of physical time. It was enough to see the pattern of the flow field and the propagation of the virus pattern too. Since we did some assumption regarding the way people were coughing and the number of particles injected each time people were coughing, I think we overestimated a bit this phenomena. I think it was traveling quicker than what it should be in reality. But since the goal was just to assess the risk of contamination, it was enough to have this answer. Then
yes.
Depends on the size of your model and the way the HVAC is working. If you have a much larger model with a very small HVAC system, it could take longer, you know, to converge and see what you want to see.
So to complete a little bit the answer, so that's for the scalar transport approach. So typically, you know, we look at a few minutes of simulation, and that's, you know, at the scale of the velocities of the HVAC system, that's already bringing the answer regarding, you know, where it's going to be traveling on the scale of the floor, just like Emmanuel was talking about. And then when we use the particle tracking methodology on its own, it's a little bit more advanced and, you know, providing a better, I'd say, a more accurate answer about the behavior of the droplets. And for those specific ones, we look more into the matter of, you know, I don't want to say a few seconds because it's not a few seconds, more a matter of, you know, around a minute or less. And those are providing, you know, enough information to see what's going on in the scale of a room or the scale of an aircraft cabin or of a vehicle. So that's, you know, depending on the scale of the building, the scale of the system that you're looking at. For example, for an airport, you will not be looking at particle tracking because it's such a large environment that you'll be looking more at scalar transport to get the answer. So
Okay.
really, it's a case-by-case problem. Yeah.
Very good. Thank you. Here's another one. The question is about modeling interaction with the contaminated surface and picking up the virus. I think you answered earlier that this is not included, but can you talk about the modeling of the virus and the contamination of the surfaces for a moment?
Yeah, so what we're looking at in the simulation is the contamination of the surface, you know, which is basically just the deposition of the droplets from coughing. There are two, I mean, well, the first assumption and the one that I talked about in the simulation, that was about, you know, how many of those droplets are actually contaminated with the virus. What is going to be the virus load of those droplets? So that's going to be the first part, and this is something we are looking further into in published literature, because we want to understand exactly, you know, how can we quantify the risk of being contaminated from this. Now, of course, if we were having this information, then we would be able to have some statistics about the surfaces and the virus load of those surfaces in terms of how much virus is actually present on what surface. And then, of course, you know, if you know what the material of the surface is going to be, I've already read some literature about what is the life expectancy of the virus depending on the surfaces. For example, we know that copper is basically really bad for the virus, which is very good surfaces for us. But then there are some surfaces where it can stay for hours or even for a couple of days. So that you could basically assess this. Now, there is an additional layer to this that we haven't really looked into. I mean, we have talked about it and we are looking into it a little bit, but it's probably a second step. It's about looking, you know, whenever you have a certain amount of viruses on the surfaces or in the air and you're breathing this, you know, how long does it take? I mean, how much of inhalation of the virus does it need for someone to become contaminated? And there is some data about the flu, because, you know, the flu has been around for so long, and so we have the information for COVID-19. There is a little less information, so we can extrapolate from flu data, but it would be still assumptions, right? So right now we're really looking into minimizing the risks, right? So you can identify a risk, and you can basically assess some solutions to minimize this risk.
Okay, very good. So 2 more questions, and I think we'll wrap. The first one is about evaporation of the smaller droplets. Do you include that effect?
No, this is not included into the model. That's correct.
Okay,
Yeah.
And the last question is, how do you both assess the accuracy of these simulations, given the fact that, you know, you may not have simulated airflow in hospitals before? Can you comment on the accuracy, please?
Yeah, so it's a very good question, and I will answer that the accuracy of the simulation will probably depend on the accuracy of the inputs you have to set your simulation. Meaning that the more accurate will be the blueprints or the 3D model, the position of the HVAC system, the ventilation rate or the mass flow you will extract or inject in your simulation, the more accurate will be the flow field, and probably the more accurate will be the way you will propagate contaminated particles.
Okay.
Yeah, and going back to this is, I mean, it's back to what I was saying, right? If you want to do a quantitative approach, it's probably better also to use particle tracking, just because it's more accurate. And we are confident in the solution because we've been using this for years in the T&M industry, and we compared it to published data when it comes to the cloud of droplets generated by a cough. For the scalar transport, we've been using it also for some applications, especially for water vapor transport. So we have some confidence in, we have confidence in the tool itself from validation against in different applications. But then when it comes to modeling, in the hospital or this type of things, then of course it's a different application. So it's like as we learn, we've been doing this for what, a month and a half. We are getting more and more information to also confirm that what we're doing is correct. And so far, all the pointers have been in the direction that what we're doing is correct.
Very good. So I think that brings us to the end of our webinar. There is 1 or 2 other questions, but we can answer them offline, I think. Thank you again, Adrian, and thank you, Emmanuel, for a great presentation.
Thank you, David.
Good luck and stay safe, everyone. Take care.
Thank you, everybody.
Thank you.